Have you ever wondered what the most extreme object in the entire universe is? It's not a star, not a galaxy, but something far more mysterious. It is a place where the very laws of physics, as we know them, seem to completely break down. We're talking about black holes. So, what exactly is a black hole? Imagine an object so massive and so dense that its gravity is inescapable. Nothing, not even light, the fastest thing in the universe, can break free from its grasp. This is the essence of a black hole. They are born from the explosive death of giant stars. When a star, at least 20 times more massive than our sun, runs out of fuel, its core collapses under its own immense gravity. This collapse triggers a spectacular explosion called a supernova, leaving behind a superdense remnant. If this remnant is massive enough, it continues to collapse into an infinitely small point, a singularity, creating a black hole. One of the most mind-bending effects of a black hole is its influence on time. According to Einstein's theory of general relativity, gravity warps both space and time. The stronger the gravity, the more significant the warp. Near a black hole, where gravity is off the charts, time itself slows down dramatically. This isn't science fiction. It's a real phenomenon called gravitational time dilation. Let's imagine a little thought experiment. Suppose you and a friend are in spaceships. Your friend stays a safe distance away from a black hole, while you decide to venture closer. For every hour that passes for your friend, only minutes might pass for you. If you were to orbit the black hole for what feels like a year, and then return, you would find that decades, or even centuries, have passed for everyone else. You would have effectively traveled into the future. It's a one-way trip. You can't go back. This effect has even been measured with incredibly precise atomic clocks here on Earth, which tick ever so slightly slower at sea level than on a mountaintop, where gravity is weaker. Now, let's talk about the point of no return. The event horizon. This isn't a physical surface you could touch. It's an invisible boundary surrounding the black hole. Once anything crosses this line, a speck of dust, a planet, or even light, it can never escape. It's doomed to be pulled toward the singularity at the center. So what happens to stuff that falls in? From an outsider's perspective, it's a strange sight. As an object approaches the event horizon, it would appear to slow down, stretch out, and fade. Its light gets redshifted, meaning the wavelengths get longer and longer until it becomes invisible to us. It would seem to freeze at the edge of the event horizon forever. But for the object itself, its journey would be much more dramatic and much quicker. It would cross the event horizon without noticing any immediate change. But its fate would be sealed. This leads us to one of the biggest paradoxes in modern physics, the black hole information paradox. A fundamental rule in quantum mechanics is that information can never truly be destroyed. Information, in this context, means the specific properties of every particle, its position, its velocity, its spin. It's the universe's ultimate record book. But here's the problem. When matter falls into a black hole, it seems to disappear from our observable universe, taking all its information with it. Then, over immense time, black holes are predicted to evaporate through a process called Hawking radiation, which was proposed by the brilliant Stephen Hawking. This radiation, however, appears to be completely random and doesn't contain the original information of what fell in. So, when the black hole completely evaporates, where did the information go? Did it vanish forever, breaking a fundamental law of physics? This question has stumped physicists for decades. It creates a direct conflict between our two most successful theories of the universe: general relativity, which describes gravity and large-scale structures, and quantum mechanics, which governs the world of tiny particles. Resolving this paradox is a huge deal. It's one of the biggest clues we have that could lead us to a new, more complete theory of everything, a unified theory of quantum gravity. Scientists have proposed some fascinating potential solutions. One idea is that the information isn't lost at all, but is somehow imprinted on the event horizon like a cosmic hologram. This is known as the holographic principle. Another theory suggests that the information escapes, scrambled, within the Hawking radiation itself, We just haven't figured out how to decode it. A more exotic idea is that the information passes into a baby universe, forever cut off from our own. Or perhaps black holes don't fully evaporate, leaving behind a tiny, information-packed remnant. We don't have the answer yet, but the search is pushing the boundaries of our understanding. So, this brings us to the ultimate question. What actually lies beyond the event horizon? What happens at the singularity? Well, this is where our current physics truly gives up. General relativity predicts a point of infinite density and infinite gravity, where space and time cease to exist as we know them. But infinity is usually a sign that a theory is incomplete. It's a placeholder for something we don't yet understand. A theory of quantum gravity is needed to describe what really happens. Some theories suggest the singularity isn't a point at all, but perhaps a Planck star, an incredibly dense but finite object. Other wild ideas propose that black holes could be gateways to other parts of our universe, or even to other universes entirely, forming what we call a wormhole. Right now, these are just tantalizing possibilities. We can't see inside a black hole, so we rely on mathematics, theory, and indirect observations to piece together the puzzle. But every new discovery, from detecting the gravitational waves of merging black holes to capturing the first ever image of a black hole-esque shadow, brings us a little closer to understanding these cosmic monsters. Black holes represent the absolute edge of our knowledge. They challenge our most fundamental concepts of space, time, and reality itself. They are the ultimate unknown, a cosmic laboratory where the laws of nature are pushed to their absolute limits. And in trying to understand them, we are forced to rethink everything we thought we knew about the universe. It's a journey into darkness that might just lead us to the brightest new discoveries in science. Thanks so much for watching. If you're fascinated by the mysteries of the cosmos, make sure to hit that subscribe button and ring the bell so you don't miss our next deep dive into the universe. See you next time.